Okay, this is for at 476. What's this? Lecture 10. Okay, I will continue with the projective varieties. So just like as remember Stadensatz. We wrote this last time, and a final Stadensatz has a bunch of corollaries, and also this has, and this projective hypersurface. So if you have a polynomial, in K x1 xn plus 1, then its zero set is V of f. This is a projective hypersurface. A hypersurface. And hypersurfaces, projective hypersurfaces, they are in a one-to-one correspondence with the forms without multiple factors. I will not go into these. And irreducible hypersurfaces, they correspond to irreducible forms. They correspond to irreducible forms. And a hyperplane, as usual, is the zero set of a polynomial of this form, polynomial of degree 1. That's a hypersurface, and if you are, this is a hypersurface V of xi. This is a hypersurface, and it's called a coordinate hyperplane. Coordinate hyperplane. This is the V of xi. This is the set of all points x1 in homogeneous coordinates, xi minus 1, and the ith coordinate is 0 because xi is 0, xi plus 1, and finally xn plus 1. So this is set of these 2 points. These are hyperplanes. So this is the hyperplane at infinity. At infinity with respect to ui. So ui, remember, is the set of all points where the ith coordinate is not 0. So this is hyperplane is projective space minus ui. So in the ui, the ith coordinate is not 0. So this is the points where the ith coordinate is 0. So let's give let's illustrate this in the case n is equal to 2. Whiteboard, next page, we have next page? Yeah, we can go back like that. Okay, so n is equal to 2. Example, if you take n is equal to 2, so let's do for the case n is equal to 1, for example, first. If n is equal to 1, if n is equal to 1, then in the, what do we have? We have this plane. Let's take field is R. Then projective spaces. Is this one, where the antipodal points are the same, are identified. For example, this point is the same as that point. Then let's see what is so when you have v of x1, this is the coordinate x1, x2, for example. V of x1 is the point where x1 is equal to 0. So it is just this point. So there is only one point in the projective space where the x1 is 0. So that 0, the point 0, 1, homogeneous. So it is 0, 1, 0, minus 1. They are the same thing, of course. So this is the hyperplane at infinity. One of the hyperplane. This is P1 minus U1. U1 is, in this case, remember, U1 is, in this case, is, this is U1. The complement of this point is U1. Of course, this is this side and the other side are the same. So U1 is, so P1 is a circle, and at hyperplane at the infinity is a simple one point, and then you just remove it. And V of x2 is V of x2 is just a single point where x2 is 0. There's only one such point. This is 1, 0. So this is V of x2 in this case. This is V of x2. This is V of x1. Okay, so let's do the case n is equal to 2. N is equal to 2. Next page. The case example. N is equal to 2. Remember, let's sketch this space. This is the x1 coordinate, x2 coordinate, and x3 coordinate. We can represent RP2 or PR2. So we are talking about PR2. So this is the lines through the origin. The lines through the origin or one-dimensional subspaces. And we can represent it like this. So this is, so every one-dimensional subspace can be represented by a point on this hemisphere, where again on the boundary the antipodal points are identified. This point is equal to that point, etc. So for instance, now in this now let's use this color. V of x1. X1 is the points where x1 is equal to 0. So it is the thing of this hemisphere. The intersection, its intersection with the x is equal to 0 plane. X is equal to 0 plane is the x2, x3 plane. So that this antipodal points are identified. So this is V of x1. of course, this point is identified that one, so that we have a circle. And let's use a different color. Next color is, let's say, this one. V of x2 is the point where x2 is equal to 0. Similarly, so it's intersection with the intersection of this RP2 with the x equal to 0 plane. So it is this circle, and this is V of, I mean this whole circle, of course. This is V of x1, and V of x3 is the point where x3 is equal to 0. It's again a circle. I mean, in this case, of course, it is RP1, and V of x3 is the point where x3 is equal to 0. It is this circle. So antipodal points are identified. These are the hypersurfaces, hyperplanes at infinity. Okay. Now, next. So suppose that V be a non-empty projective variety. In Pn, so that, as we know, then in this case, its ideal is the prime ideal, as we saw in the example. It's also a homogeneous ideal, of course. Oops, this is not non-empty. Then, if you look at this gamma HV, so if you divide the polynomial ring by, as in the affine case, if you divide by IV, we get an integral domain. This is an integral domain because this ideal is prime. This is called gamma H is called homogeneous coordinate ring. Homogeneous coordinate ring of V. How do we see time? Properties. I did not look at the time. I hope I can finish on time. Okay. Suppose now, suppose that I be a homogeneous ideal. Ideal in K x1 xn plus 1. Typically, it is the ideal of a subset of Pn. So that is, so remember, what's the homogeneous ideal? So if you take a polynomial, if you write as the sum of forms like this, where this Fm is the form of degree m, Fm plus 1 is the form of degree m plus 1, etc. If such a form is in I, then each Fi, Fm, Fm plus 1, they're all in I. So that's homogeneous ideal. Typically, for example, this zero set of a subset of projective space is homogeneous. Okay. Now let's define gamma to be kx1 It's n plus 1 divided by this ideal. And an element f, an element, so element of f in gamma, which is f is the left coset of some polynomial. This is called a form of degree d if there's a polynomial f, if there's a form of degree d if there's a form of degree d, there's a form f such that f can be written like this. Okay, so this is, so there's a form of degree d like this. Let's see if, so claim that this is well defined. So namely, so there's a form f such that f is equal to f plus di. And they're also, yeah, they are also a form of degree d. Okay, this is, there's a form like this, so not necessarily degree d. And here is, so let me make it precise. Yes, f is a form of degree d, capital F, in the previous. So this capital F is a form of degree d. Okay, next. New white block. Okay, now this is well defined. If f is not 0, if f is not in I, so the reason is that, so if f is in I, this, if we have two different representatives, such that degree of f is the same as degree of, so degree of f is, degree of f is I, and degree of g is j, so let's say, two different forms, then since their classes are the same, representing f minus g is in I, and since I is homogeneous, this f is a form, g is a form, then the degrees of f and g must be the same. The reason is that, so degree of f is equal to degree of g. The reason is that if they are different, if degree of f is not equal to degree of g, meaning if I is not equal to j, then f minus g in I implies that f is in I and g is in I. So that means f plus I is equal to I. Oops. So that f is equal to, so that in fact f is equal to 0 in gamma. And so that's contradiction because we assume that f is not 0. So therefore I is equal to j. oops, I is equal to j, not I is equal to j. So that therefore degree of f is well defined. So namely, if we take an element of this ring, so what do we have? Oops, why do we do it? That's good. So so in this ring gamma, gamma is kx1, remember, xn plus 1 over I. So if we have an element f, which is f plus I, we said that this f is, little f is a form of degree d if there's a form like that. There's a form of degree d like this. So if you choose another representative, this its degree is also d, another representative of f. Okay, next number 9. Okay. Here's a proposition. Next whiteboard. Proposition. Proposition: if f is in gamma, then f may be written uniquely as follows, as f is equal to f0 plus f1 plus fm, where fi is a form of degree I. Or 0. Or 0, of course. Proof, here's a proof. So if we write f as, if capital F represents little f, then this f can be written as f0 plus f1 plus f2 plus f of m, where either degree of f of I is I, or it is 0. So any polynomial can be written in this form, like this. In this case, f is f plus I, which is f0 plus I plus f1 plus I, it's left coset, and fm plus I, and that is this is f0 plus f1 plus fm, so that each fm is each fi is either 0, namely if f1, for example, f1 is in I, this f1 is 0, that f1 is 0. Otherwise, this f1 is a form of degree. This fi is a form of degree I, and this is the existence. And here's the uniqueness. Suppose we can write another way like this. We can write f as also the sum of gi's, where gi is the left coset of capital GI. Then in this case, then f is the you add up these GIs and look at this left coset. That is f is represented by also sum of GIs, and it's also equal to sum of just f plus I, because f is another one representative, G is another representative, so that f minus the sum of Gi is in I, namely f0 minus G0 plus fm minus Gm is in I, so that these are the components of degree I. So parts of degree, so homogeneous parts. So that since I is homogeneous, each of these terms must be inside I. So that fi minus Gi is in I for all I. So that fi plus I is equal to Gi plus I. So that means fi is equal to G of I. So that f0 plus blah blah fm is equal to G0 plus Gm. So that the representative is unique like this. Actually, I don't need to write. I don't need to write this last part. So remember. This proposition works also. This proposition works for I is equal to IV. Namely, we can take I to be the ideal of a subset of Pn because where P is a subset of V is a subset of Pn, because this I of V is always is homogeneous always. Yeah. Okay. I guess this maybe red is better. Let me use red. Now let V be a projective variety. Then we have this gamma V, namely this kx1 xn plus 1 over IV. I is equal to IV, let's say. And so this is an integral domain. So we can look at it as its field of fractions. So let KHV be the field of fractions. Fractions of this gamma HV. So namely, this is KHV is, remember, you look at the left cosets of I, you take the formal sums. So that where the denominator is not 0, G is not in I, right? Okay, that's the field of fractions of gamma H, gamma V. Next page. So this is, if you take an element, if if you take an F in K, F plus, if you take a polynomial, F plus I is in gamma H, right? Then this is gamma H is a set of F plus I such that F is a polynomial. Kx1 xn plus 1. Okay, so if you take such a representative, if F is not constant, it's capital F, not little f, capital F is not constant. If it's not constant, then it is not defined at so suppose that it's not constant, and if you take p to be a1 an plus 1, so then the p also represents by so then f of lambda a1 lambda an plus 1, that's another representative of p. And if you look at the a1 an plus 1, this is lambda to the some d times a1 not sorry, any polynomials, and not any. So they are not equal. They are not equal for all lambda. So therefore, if f is not constant, f plus, or this little f plus I is not defined. Is not defined at p. So you cannot define f of p. But how do we define this? How do we define? So let me give some example first. So let f is n is equal to 2, and let f is x times y, the left quadrant of x plus y, and in the denominator x squared plus z squared plus I. Say p is equal to a1, a2, a3. Then if you take any representative, then f of, let's say, lambda times a1, lambda times a2, lambda times a3, this is so a1 times a2 over lambda squared times a1 times a2 over lambda squared times a1 squared plus a3 squared. If we define it like this, a1 times a2 over a1 squared plus a3 squared, it is independent of this definition. Is so if I define f of p to be, I define f of p to be this a1 times a2 over a1 squared plus a3 squared. It is independent of the choice of the representative of p, and also it's also independent of the choice of the representatives. When p is in I, I, then it is also independent of the choice of this left coset of x plus y. I mean, if you choose another representative of this xy plus I, so you can also write this xy plus some g plus I, where this g is in I, then of course, since g will be 0 at the point P, it will not affect this definition. So that this form, this quotient, is well defined at the point P. Okay, so that if f and g are the forms of the same degree, then we can define this, we can define f over g on at P. Well, how do we define? We just, because the reason is that f of a1, if you take at any point any representative. Any representative is lambda times A1, lambda times AN plus 1. To take some representative, of P, it is G over lambda times A1, lambda times AN plus 1. For the same representative, of course, this is some lambda to the D. If they are degree D, lambda to the degree D of A1 AN plus 1 over lambda D G lambda D G A1 AN plus 1. So they will cancel, so that this quotient, if we define f over g at P as f of A1 over A1, f of A1 AN plus 1 over g of A1 AN plus 1, it's well defined. So that it is well defined like that. So that f of g is defined at P, as long as f and g are forms and they have the same degree. And this prompts this definition. The function field of V field of functions, function field of V is defined as K of V like this. This is the point Z's in KHV. KHV, remember, the quotient of gamma H. This is such that C is equal to F over G. So these are F over G. F is the left coset of some polynomial. G is the left coset of some polynomial. Where F and G, where F and G are forms of the same degree. Same degree. So namely, they are represented by the same form of the same degree, if you like. Okay, this is a field. This is a field. This is a field, and this KV is a subfield of KHV. It's not a field of fractions of gamma H, of course, and it is this KV, because the constants are defined at every point. Constants are defined as a function at every point. If you like, it is a quotient of a form of degree 0 over degree 0. Okay, KV, and it's also inside KHV. And let's note that this gamma HV is not inside KV. They cannot be defined at the points of V. Elements of KV are called rational functions. And we, for example, as we defined above, for any point, this x squared plus y squared plus I, at the zero set of I. So if you, this is IV, of course. If you take a point at IV, this x, this function, this z, can be defined at that point. So this is in KV. This is denominator z squared. Okay. Next, let's see if P is in V, Z is a point is a function is a function on V, rational function on V. Then the Z is defined at P. Z is defined at Z. Let's say Z is equal to f of g, small g, defined at P if this G of P is not 0. So G is, remember, this is G, something like G plus I, so that this I, this capital G must be defined, should not be 0 at P. Okay, so just like is in the affine case, we define OPV as the point Z is equal to F over G in KV, such that Z is defined at P. Namely, G of P is not 0. It can be defined. So this OPV is a subring. It's local. It's maximal ideal. As in the affine case, its maximal ideal is, so it's a local ring. So its maximal ideal is MPV. Let's stand it like this. It is the F over G such that G of P is not 0. So F and G, F over G is not 0, but since F of P is 0, so that it is not invertible. So these are the, just like in the affine case. And here's the definition. This OPV is called the local ring. The local ring at P. Okay. Let me just comment also on projective change of coordinates. Change of coordinates. So if you take a linear isomorphism, so if this from this vector space to itself, if we have an isomorphism, linear change of coordinates, remember in the affine case, change of coordinates are, these are isomorphisms, plus it has also translations. In this case, we don't have translations. This is an isomorphism, linear isomorphism. If this is a linear isomorphism, this induces, so if you have a one-dimensional subspace of an plus 1, then it maps to a one-dimensional subspace of this an plus 1, so that one-dimensional subspace is a point in Pn. So namely, if you take a point in Pn, it maps to a point in Pn, so that you have a well-defined map like that. If V is algebraic, then its inverse image is also algebraic. Or its image is also algebraic. And let me finish here. Let me finish this lecture here. Okay, let's end this.